Welcome up to LG Egret and the Urban Training Center here at Marine Corps-based Quantico. My name is Steve Chasirik. I'm the AACUS Program Manager at Aurora Flight Sciences. Again, I think we're going to have a really nice day today for this event. A lot of distinguished visitors here, General and staff. Yes? Oh, all right. There it goes. Perfect. All right. And so, with that, we have a number of, we have some initial briefings that we're going to go through, and then we'll have the flight demonstration, and then we'll lead down to a static display later on. So what I'm going to do right now is introduce Dr. Jones from ONR, and he's going to get us kicked off. Dr. Jones, thank you.
All right, well, good morning. We'll hope the microphone stays with me here. Good morning, General Neller, Ms. Kaufer. Glad you could join us. Lieutenant General Walsh, Lieutenant General Dana, other general officers, and there are many, and senior executives, ladies and gentlemen, welcome. Okay, right up front, it is cold out here, and it is even colder out there. So we're going to enjoy each other in here for a few more minutes. But thanks to all of you for braving this biting cold to join us here today for the final demonstration of what we call the Autonomous Unmanned Aerial Cargo Utility System, affectionately called AACUS. This ONR Innovative Naval Prototype was commenced in response to an urgent needs statement submitted by the Marine Corps just a few years back. Now, this is key. Please note that this is more than just an unmanned helicopter. AACUS is an autonomy kit that can be placed on any rotary wing platform and provided with an autonomous capability. It has a software package that enables it to make mission decisions on its own. It has a suite of sensors that allows it to get information from the environment to inform its decisions. And it is pushing the envelope on autonomous capabilities. Now imagine for a moment that you're part of a Marine Corps company deployed in a remote location in rough terrain. Imagine that for a minute. I think I've got it. I think I've got the feeling. You're low on supplies, you're low on ammunition and water and batteries or even blood, and you have placed a request for resupply. Now the roads are dangerous, the weather is bad, and you may not be able to get a logistics truck to your site. But an AACUS-enabled helicopter can respond to the request. It can navigate to the location even in a GPS-compromised area. It can determine the best location for a safe landing without the need for a forward ground control station, and do all of this in low visibility conditions. Now, the Office of Naval Research is deeply involved in the technology of autonomy. We're also working with autonomous unmanned aerial systems, autonomous unmanned surface ships, autonomous unmanned swarm boats, and various autonomous unmanned underwater vehicles. We made AACUS an innovative naval prototype, developing the technology ahead of requirements as an example of true technology innovation. While it is targeted right now toward Marine Corps needs, those needs are not really unique to the Marines, and in fact we have representatives here from the Army and the Navy with us today who are also interested in these similar capabilities. Equally importantly, the AACUS system is a product of partnerships between ONR, the Marine Corps, Aurora Flight Sciences, which is now a subsidiary of Boeing, and our primary partner in this development. But they've been assisted by Carnegie Mellon University, Rockwell Collins, Near Earth Autonomy, and Cutta Technologies. There is infinite value in having operators, engineers, and scientists all working closely together to develop asymmetric advantage for the joint force. So I'm really proud to be here today with so many men and women in uniform, and I see all of you out there. You go into harm's way on our behalf every day. Thank you for your service, and the Office of Naval Research exists to ensure that you folks are never in a fair fight, to ensure that you always have the edge. It's now my distinct honor to introduce Lieutenant General Walsh. He's the Marine Corps Combat Development Command and also Deputy Commandant for Combat Development and Integration. Ladies and gentlemen, General Walsh, sir.
Good morning, Commandant. Just very quick, thanks, Dr. Jones. Really, the first thing is appreciate the partnership that you've done with our team to move this program forward. It's been a very deliberate but solid approach. You've developed a great capability in some ways ahead of our requirements and moving out on this technology. And now it's up to us to figure out how we're going to use this. So fantastic work. And what I would just look at this is you touched on autonomy. And I think that's the key thing today is looking at this is one capability that we're moving out on very quickly from a logistics capability to get logistics out to our Marines. If you look at our Marine Corps operating concept, operating in a distributed manner in the future warfighting areas, this gives us that capability to distribute quickly and move logistics forward in an autonomous way. And as you said, autonomy is the future of where we're going. And it really ties into man-to-man teaming. And that's going to be our advantage in the future, is man-to-man teaming. How we use machine learning, artificial intelligence, this capability of cognitive autonomy is exactly where we're going. And I would just say the young Marines today, the Marines, for example, that we just did in Sea Dragon Phase 1 with 3rd Battalion, 5th Marines, and Commandant, we're getting ready to bring you the recommendations coming out of 3-5. What we did see is those young Marines that grow up in this tech-savvy, free-thinking society, this is our advantage. This with our warfighting centers, this with ONR, DARPA, and industry is really what our advantage is. And we've got to keep pushing to move this stuff forward. Commandant asked us, where are we going to go next with this? Well, what we're going to do next is we're going to put it in hand in Sea Dragon Phase 2, which is going to be focused really on our logistics effort with General Dana. And we're going to get this out in Phase 2 with CLB, our Combat Logistics Battalion 8, out in ITX 3-18. So we're going to take capability, we're going to put it in the operators, we're going to get it in their hands, and we're going to see how this, a lot of people look at this as like KMAX. Marines have done great work with KMAX. This is completely different than KMAX. This is using autonomy, and it's where we want to go with autonomous capability. And so I think that's what we're going to see today is now really stepping into autonomy, which is different than controlling this, from the ground and using man capability across the board. So I think this is the light bulb coming on. This is one snippet that I see where we're going to go across the board, and we're going to need lots of support to continue to do this. But I know the young Marines are going to drag us in this direction. So thank you very much.
Welcome everybody. I'm program manager, and I'll give a little bit of a geek presentation maybe, but it'll also try to connect what we do, what we're doing at AACUS for 5 years, to where we want to go in the future and where I know the Marine Corps wants to go. As Dr. Jones mentioned, this is an INP, Innovative Naval Prototype. What I call them is big bet efforts. At the time, we were responding to an urgent needs statement, but we also, through their INP process, had the vision to say autonomy is going to be important. We know it's going to be important, so even though we didn't have at that time a program of record or anything like that for it to go into, we said we know this is going to be for the future, so we put what I believe is the largest autonomy program in DoD to capitalize that well. It wasn't focused to be an airframe, it's not a UAV program, and it's all about autonomy. The S&T focus at the beginning of the program was to provide cargo to austere landing zones, but different from what you would do in UAVs today. You know nothing about that. You have no digital maps, you have no GPS, you want to be able to avoid obstacles en route, as well as when you get to the landing zone and do all that without GPS. And one thing we also added to it, we learned a lot of things as we went through. We learned we could avoid wires. We could, if you've been in combat, there's wires strung everywhere. You're trying to land helicopters, and we figured out we could also detect wires. We also added capability, and you don't really see it today because the aircraft would have to do a pedal turn probably to fly out of when it lands amongst the buildings over there. We're showing today that we can do multi-vehicle, on one mission, we can do multi-vehicle landing zones, as well as in confined spaces. So it'll land inside the walls down there autonomously of the FOB site, as well as amongst the buildings here. Nobody else is doing that. People talk about it, people that say we could do it or it's right there, but this program, ONR capitalized it well enough to get it to that point where it is right now, where it can go into experimentation. We can start proving out with the Marines those capabilities. And one thing I found, I was a naval aviator myself, is CONOPS really means a lot on autonomy. You need to know what's happening and how, and when you build the autonomy, our motto is fly like a pilot. So we wanted the Marine on the ground, you'll see the Marine we have Marines we trained in less than a day. They'll do a request and that airplane will come to them. It could be a manned aircraft, it could be an unmanned logistic aircraft, but it's completely autonomous, and it'll fly to the landing zone just like a pilot would. So we don't mess up their ConOps, and that was a big part of the program. We wanted to make it where we didn't disturb and put more burden on the MACTAP commander. Right now, with a more distributed force, this will allow us to build a task, a helicopter or unmanned logistics UAV to go to any LZ with no infrastructure. You don't have to send a team in ahead of it, put people on the ground. We're using basically an app on a tablet. But we've also demonstrated a few weeks ago with our Army brethren that we can repurpose a PRC-117 to control this vehicle. So it takes no, we trained the Marines you'll see that are operating today last week and a half a day. They can operate the vehicle because the autonomy gives us the ability to for them not to have any aviation knowledge. It flies to the landing zone. It avoids obstacles. We make it where it can go to the landing zone and land on its own, or if we tell it to when it takes off by consent. Another part of the program that you'll see, these are the things I'll mention because they're not obvious by watching it, is that the planning goes on board the aircraft. We give an operator, what we call an operator, just takes commander's intent. Where do you want to deliver it? What do you want to avoid on the way? Maybe you have some mandatory waypoints. But it sends that, what we call commander's intent, to the helicopter, and the planning goes on board there. People don't do that. Everybody's used to this awkward GCS that does all that. And then you give it permission to go, and it goes. We can go to multiple LZs. That's what we demonstrated today on one mission. And we're able to do that all autonomously. It's avoiding things en route. And what's amazing, and this is what almost is scary and amazing at the same time, we also said we're not going to pour money into sensors. This is COTS. We bought everything here you could buy on the open market as far as the hardware that's on here, which is scary in a way because when you consider our peer competitors, this technology is out there. So we've got to get the cycle time, as the general mentioned, get it into experimentation, and at the same time be pushing that technology, getting that really immediate feedback from the Marines and keep the technology flowing, or if we get into this very serial cycle time, it's going to be a problem for us. And the other thing not to mention, as you see what's going on here, that this all could be put on a manned aircraft as a pilot aid also. We have the ability that this gives it with a digital flight control system that we put on it as part of this, and the ability to map the ground and remember where the ground's at. It gives you some DVE, diminished visual environment capability, where you may have a lot of dust in the air. So it's not, when we talk about autonomy, people first think, oh, it's unmanned, but this autonomous flight control is really what we're talking about in a manned or unmanned aircraft. So just as you're looking today, that's why I wanted to make a few statements. This is end-to-end mission autonomy. We're doing an entire mission, and we're doing it on a full-scale aircraft. You look at a lot of the YouTube videos, you see poised, flying around, but this is a hard mission. Things really crash. Without our good partners like Aurora, they've got the processes that we've used to be able to do that on a full-size helicopter. So we were tasked to be able to go do a no-hover landing to an LZ with no infrastructure on the ground, no GCSs. It gives flexibility to the MACTAP commander, but it's intuitive. Like I said, we train the operators. The Marines we have on the ground aren't people. We didn't groom anybody. We picked some people that we were given, and we were able to train them in less than half a day. And really, we set that for 30 minutes, but we also were training people to get things in and out of the helicopter. So it was a little bit of additional training that would be part of our system. So with that, I'll turn it over to Steve Jasaric, and and what we're going to do, just so you know, we're going to start, when we start flying, we'll take a little break, and we're going to raise the walls. Get your cold weather gear on, because it'll probably get pretty cold in here then, but that'll allow you to be able to see what's going on the screens inside the cockpit, but then you'll be able to see the helicopter as it's landing also.
Thank you, Dennis. Again, welcome. Good morning to all. Again, I'm Steve Jasaric, the AACUS Program Manager at Aurora. At this point, I'd like to point out some of my senior management here. I have Dr. John Langford, our Chief Executive Officer. I have Dr. Matt Hutchison, our Chief Operating Officer. Also with us, I believe, we have Tim Hannafin from our parent company, Boeing. Thank you, Tim. Welcome. So he's down from our DC office. Now that I think everyone's aware, we are a Boeing team company, and so it's quite interesting. So it's a lot of other opportunities are opened up now with larger OEM being affiliated with them. So with that, also I'm going to ask Matt, our Chief Operating Officer, to step up here in a minute, but I also want to point out a bunch of our subcontract team partners, Sanjeev Singh, Sebastian Schur from Carnegie Mellon, Sanjeev from Near Earth Autonomy, major contributors to the program over the years. Ben Russ and some of the Rockwell Collins Controls team is here. Again, flight control system on the aircraft was a major undertaking working with those folks, and we've come up with a really good solution. Also here we have Cutta Technologies. We have James Bona with our tablets, our field operating handhelds. And we also have some of our more recent partners from Silvis and Sistel who help with a lot of the communication on the aircraft. So with that, I would ask Matt if you want to say a couple things, and I'll jump into our briefing.
Good morning. My name is Matt Hutchison. As Steve just said, it's a real privilege for me to be able to say just a couple of words to such a distinguished audience and to a number of really distinguished colleagues in both the industry team and the government team. As Dr. Jones referred to at the beginning, this has been a multi-year effort. We're at the tail end of this innovative naval prototype program. It has been an exemplary partnership between the government team and the industry team. It's been a real privilege for our folks to be a part of that. It's a very interesting and difficult technical problem, and so we are substantially an engineering company. We've been very, very focused on pulling the different system elements together over a multiple month exercise program over the last portion of this year. It's really today is kind of exemplary of what we are aiming for, and that is you put all of the technical pieces together, you move from simulation into test, and you start to see what it can actually do. We are at that stage of the program. We are really excited about the opportunity of seeing what this technology can do for the United States Marine Corps, and are really excited about being here today to do that. So thank you for your time, and really appreciate your support of this program to this point and beyond. Thank you.
Yeah, from a program overview standpoint, a lot of this Dr. Jones and Dennis Baker had iterated, but I think a takeaway from the IMP is that the urgent needs statement was generated by Marines for Marines. Again, and having an unmanned capable asset that they can use to move large logistics supply equipment back and forth. So, that really drove us, and drove the AACUS program. It's a rotary wing mission system kit. It just happens to be currently on an H-1H. And again, we've moved it on numerous other aircraft. I'll touch on that in a minute. But essentially, the system enables intelligent autonomous landings and to steer locations, right? So the system makes a decision, picks the safe location for it to put down. And you'll see some of that today as it's going on, and we'll have live video streaming. So Fritz Langford, our chief engineer, will go through that. Again, the system will plan to an ASR. The tablet, the Marine in the field will issue an order to send something to them and complete the mission. The aircraft on its way to that location will avoid obstacles en route, and again, assess the landing zone and make a safe touchdown. No required special training, right? I mean, you'll see Sergeant Jones has been working with us. He's pretty much a pro at this now, so quite interesting. And again, it was designed with open architecture. About a year ago, we did testing with the PMA 281 Common Control System, where we went from our ground control station that we developed with Aurora, and we used the NavAir system. And so that was one of the main building blocks and pillars for this program, is to ensure it had an open architecture. Okay, so the program timeline, right? So from my standpoint, here we are at the end of the IMP, right? This is the final contract milestone for the effort. Again, there's activities we're working together with ONRs from final reports and other transition type activities of what we'll do. But the big emphasis here really is that it'll drive and transition into concept-based experimentation with McWill, right? ITX, Combat Dragon is the first one we've talked about. We're finalizing, working closely with the team there and trying to get that in place, so we have some overlap between the end of the IMP and the pickup of this operational training. So with that, we kind of envision there'll be a lot of operational training. There'll be reports, lessons learned, assessments, which would then drive and drop down to what we're going to do for technology maturation, right? It's not, we're going to have to decide what that'll be. That'll help drive ConOps, future ConOps, and future requirements for what's the autonomy package look like on a future aircraft, right? So this is a very key element of continuing forward for future autonomy programs, that being MUX. And so what I want to note here was the Marines are the first ones taking the aircraft and using it in an operational demonstration. And a lot of interest and a lot of conversation with NavAir. We see the NavAir Cure program, which is they want to do some sling loading and deployment of EOD robots. So it's teaming an S&T autonomy program with the autonomy program we currently have has transitioned out as AACUS. NavAir and ONR have the Sailors program doing some shipboard based activities and landing approaches. Again, they're coupling different technologies that are in work that the government has paid for. So this is a value in continuing moving forward. And also a lot of interest from the U.S. Army, the telemedicine group, TACTRIC. We had done a small demonstration with them called Dial-A-Drone. Very successful. Dr. Gilbert on the TACTRIC side was very interested. I know he's having a lot of dialogue with the ONR teams, Dr. Bentley, and I believe Dr. Mason. Code 34. So a lot of synergy happening now, and it's, in my mind, we're heading in the right path. Operational based training and experimentation, and again, I think the General, you pointed out the manned-unmanned teaming aspect is what's going to happen here over the next couple of years, and I'll have a set of requirements that we can then define what the future of autonomy aircraft will look like. So with that, I will turn it over to Fritz Langford, the Aurora Chief Engineer, and he'll talk some technical aspects of the system. And Fritz. Thank you.
Thank you. My name is Fritz Langford. I am the AACUS Chief Engineer at Aurora Flight Sciences. And I'm going to talk just a little bit about about some of the technology that we've developed on the program. There's a lot more that's not in my slide deck. So and I don't want to talk for too long because I know that you guys came out here to see the airplane fly and not to watch me talk. There are booths around the back of the tent as well. So when we do the flight demonstration part of this event, I would encourage you to walk around, talk to other members of the team. We have SMEs for each of the things that I'm going to talk about. Available. We have little booths, we have videos, we have physical artifacts from some of the prototypes that we've built back there as well. So for everything that you see and everything that's on the aircraft, we have a static display here as well to talk more about if you're interested in it. Okay, so one of the things that Steve and Dennis mentioned was that this program was built as a platform agnostic portable mission kit that can go onto any aircraft. And so scalability and the autonomy architecture was a big part of enabling that. And one of the big things that we considered in designing the system was trying to make each piece of the autonomy architecture generic to enable it to be used and reused across multiple platforms. So in particular, the planning algorithms, right? That was a big part of the research that was done by Carnegie Mellon and by other members of the team in making the planning algorithms generic, looking at the different sensing modalities across different aircraft with the sensors. As Steve mentioned and Dennis mentioned, they're off-the-shelf sensors. We didn't build new sensors for this program. And then attaching them all together with vehicle performance models that basically is a digital version of the pilot's operating handbook, right? So that you know what the aircraft is capable of. You have a sensor, you have portable planners, and you can attach them all together and come up with a robust system that is portable with maximum reuse onto new platforms. And the autonomy that's on board, this is autonomy is a big topic, and so there's a lot of pieces to it. But at its core, this is the cycle that the aircraft is doing here. That it's interacting with operators, it's taking input from the humans at a high level. So something like where you want the aircraft to go, really. So start here, fly over here. The operator can input a few tactical control measures. So a no-fly area, or a heading to fly if you're at an airport or another controlled airspace, and then also supervisory control in the form of execute a wave off, execute a landing, or execute a takeoff, right? So these are all commands that are easy to talk about, but historically operators have had to have a significant amount of platform of domain knowledge to communicate their intent to the aircraft. So things like waypoint planning, things like vehicle performance parameters have been things that the air vehicle operator has historically needed to know, or able to actually fly the aircraft. Right, a remote pilot on the ground moving the joystick. We don't have any of that on AACUS. Right, what we have is an operator on the ground with a mouse and keyboard who is saying, start here, fly over here, and the aircraft is doing all of the planning, and it's doing all of that on board. And then we have a sensor on the front. The main primary sensing unit is mounted on the nose of the aircraft. There are a few other additional sensors underneath the belly and on the tail boom. And those sensors are enabling the aircraft to map out the world around it so that the planners can react to the world and plan through it safely. So they're detecting hazards in flight, trees, wires, and then also objects in the landing zone. So objects in this demonstration, we'll use a Pelican case as an object that's in the landing zone that we want to identify and then maneuver the aircraft to avoid landing on top of it, landing in an unsafe condition. We're also evaluating for other hazards in the landing zone. So a lot of the research that's been done on the perception side has been looking at other hazards, right? Things like mud, things like water, inside of the landing zone to evaluate the surface and ensure that the aircraft is landing and operating in a safe environment. And then finally, all of that ties into actually being able to fly the aircraft, right? So having at its core a fundamentally robust flight control system and able to do very detailed motion planning to control the aircraft, to maneuver the aircraft through the map that we're building with the obstacle detection system. And then do that loop again. Go back, check to see if the human has more input. Maybe the human has changed his mind. Maybe he wants the aircraft to fly over here instead. Maybe he wants the human to do the aircraft to do a wave off. Right? There's a button on the tablet for a wave off. Press the button and iterate the loop again. Right? So take the input from the human, check to make sure that it's safe, and then operate the aircraft and execute that loop. Okay, a big part of our philosophy here is fly early, fly often. So that means getting the technology out and onto the aircraft and into a place that we can test it fairly quickly. So what you'll see today is that there is a safety pilot on board. That this is what we call an optionally piloted aircraft, but there is a safety pilot on board. And there are a couple of reasons for that. One is that the aircraft is, that this program was focused on autonomy rather than on purely autonomous operation. So this particular aircraft is single engine, and it has a single string flight control system, so there's no built-in redundancy. It's fairly robust, but when you do the FMICA analysis, what that flows into is obviously not a level of robustness that could be achieved with some redundancy. The other thing is that we have not automated something like the engine control on this aircraft, right? So this is about detecting obstacles and flying the aircraft. This program was not about automating engine start and engine management. So the safety pilot is doing that. And then the third thing that gets us from having a safety pilot on board is that the pilot is able to take over in the event that the autonomy system isn't quite together. So our pilot, Jason Jewell, often refers to this as being like a student pilot. That the system mostly does the right thing, and occasionally you have to kind of coax the student teach the student to do the right thing, to fly like a pilot. And a great example of that is today in the wind conditions that are out here. So the forecast today was for winds of 15 to 18 knots. It's actually a bit calmer. Manassas is calling 8 knots right now out of the west. Our flight control system was designed for 20 knots, so we're okay. But we don't have to have a hard wind limit on this aircraft because we have a pilot on board who can monitor the system, who can watch that it's doing the right thing. And if we have an actuator disengagement, if the command isn't tracking if the actuator isn't tracking the command, the system will alert the pilot, and the pilot can take over. And so that's we have levels of safety built into the system, but also by having a safety pilot on board, we can do rapid envelope expansion in a safe and efficient and cost-effective manner. Okay, so what we're doing today is right now we're doing the program overview. After this, when I finish up in a few minutes, we'll take a quick 10-minute break for coffee and for, as Steve mentioned, to move the TV out of the way, roll up the sides of the tent, and then give some of our public affairs colleagues some time to get down to the LZs. And then we'll start doing the flight demonstration part of the event. So all of these screens will have live video coming in from the two LZs, from the forward operating base and from LZ Egret. And then we'll also have video downlink off of the aircraft showing both 3D and 2D views of what the system is doing as it's detecting obstacles, as it's planning a path for the aircraft to fly, and as it's operating the aircraft. And also a view of the cockpit so that you can see the pilot has his hands in his lap, or that he's guarding the controls as he would for a student pilot. Okay, we're going to do 3 missions here, which will all of them will start about 2.5 miles north of here, up at LZ Stork, which if you drove in on Tokyo Road, you drove right past, and the aircraft will start up there. We'll plan a 2-hop mission from LZ Stork down here into LZ Egret, into the bowl right behind us. The aircraft will map out the landing zones, search for hazards, identify the buildings, select a safe area to land. And then as the aircraft is flying, it's going to do all of that on its own. That the human will have input at the beginning. He'll select the starting area, the ending area, nominal location to land, and input his tactical control measures, a few headings to fly, and then also a set of safe flight areas and no-fly areas over some of the other ranges today that are hot. And then that's it. Once he clicks launch, the aircraft will execute the mission autonomously, and that the human interaction after that is optional, that the system is capable of completing the mission on its own, that the lost link behavior on this aircraft is to finish the mission. It's not to execute an RTB or a predefined profile. We've added that in. We have found that some operators like that, and in the event that some of the sensor dies, that is a behavior that the aircraft can execute to do an autonomous return to base. But it's not the default. The default is to continue the mission, is to continue the resupply mission, and get the supplies to the Marines in the field. And then once it's in the LZ, we'll have the tablet operator, Sergeant Jones, will utilize the tablet, command to take off. The aircraft will take off and execute the autonomous return back to LZ Stork. And then we'll do that again, heading into the forward operating base. So that'll be a fairly similar mission here, into a different environment. So we'll watch the system operate in the forward operating base. The forward operating base is interesting because there's also a tree line on the departure path. So we'll watch the aircraft deal with that, detect the tree line, plan around it, and execute its takeoff. In both of these, we'll be unloading cargo, so we will have Marines in the landing zone that you'll be able to see on the video streams, approaching the aircraft, unloading cargo, and then the Marines with the tablets commanding the takeoff. And then we'll do a third mission back here to LZ Egret. In this case, we'll have an obstacle in the landing zone. We'll have a Pelican case out here today. The aircraft will identify the obstacle in the landing zone, plan a safe trajectory, and land, and again, safely operate the aircraft. We'll also have the tablet operator command to wave off, right? So So the idea is that the tablet operator's inputting his intent. There's a button labeled wave off. He doesn't have a joystick. He doesn't have to drag and drop a bunch of waypoints. He just has to tell the aircraft to do a wave off, do a go around. The aircraft will plan and execute that on its own. And then we'll shut down for static display. The test pilot, Jason Jewell. Jason is a Marine reservist and a V-22 test pilot. We'll say a few words down in the LZ egret. We'll have a chance to do a walk around on the aircraft and also have time for some Q&A. And finally, before I finish here, I wanted to echo the comments that Steve and Dennis had made, that this is really a team effort, that these projects are enormous, and a lot of people have worked really hard on this over the past 5-6 years for some of us. And I wanted to recognize them again and to encourage all of you to visit the booths in the back of the tent to see up close and personal some of the static displays and the video products and the prototypes that have been built on this program, and to recognize the just enormous amount of research that has been conducted on this program that has gone into this being a functioning prototype. So, all right, so thank you very much. We're going to take a 10-minute break here. We'll reset the tent. We'll roll up the walls.
All right, ladies and gentlemen, I'm Bob Freeman, Public Affairs for the Office of Naval Research. Thank you for coming today. We have availability, so you can ask questions to some of the technical people on this project. This is Dr. Fritz Langford from Aurora Flight Sciences. Mr. Oh, I'm sorry. Mr. Fritz Langford. Let's correct that. And he's you're the Aurora lead for this program?
I'm the chief engineer for the program at Aurora Flight Sciences.
Chief engineer. Next to him, Lieutenant Colonel Schmidt from the Marine Corps Warfighting Laboratory, to be able to give you a Marine Corps perspective, not only on what this is, but where it's going next. And then next to him is Corporal Osterhaus, who is one of the tablet operators, who can talk to you about it from his perspective. And at the end of the table is Mr. Dennis Baker, the program manager of this project for the Office of Naval Research. Yeah. Can I ask you all how you would like your name to be represented?
Speak loud and into the mic.
Sure. Fritz Langford, F-R-I-T-Z. L-A-N-G-F-O-R-D.
Lieutenant Colonel Dan Schmidt, S-C-H-M-I-T-T.
Christopher Osterhaus, that's O-S-T-E-R-H-A-U-S.
Dennis Baker from Office of Naval Research. Dennis, D-E-N-N-I-S, Baker,
We have one additional.
One up here. Okay, I guess I'll join the gang. Master Gunnery Sergeant Chris Hansen. I work at Headquarters Marine Corps Installation and Logistics.
Dennis, can I ask you just to open it up and say a couple
Loud.
words?
How
How did it go today?
I thought it went really well. I was pretty exhausted running around talking to so many people, but I think the system behaved really well. I think the operators, just like we expected to operate with the Marine Corps, where it was something very intuitive to operate, something that could handle. We were expecting even worse winds, so it was able to handle winds. You saw that it made a pedal turn, things like that, where it acts like a pilot would act, which is one of our goals in the program. And so it went very smoothly, I think. And I'll let the operators, they were out there using it, let you tell you, but I thought we were approaching their objective. We worked with the program to be able to do a multi-mission mission, go into confined spaces, and operate safely.
Colonel, would you like to say something introductory?
Lieutenant Colonel Dan Schmidt from the Marine Corps Warfighting Lab, and really what I can talk about is the so what of the technology. Not an engineer, not a scientist. I'm an infantry officer that's responsible for the live force experimentation for the Marine Corps. We have a campaign we call Sea Dragon 2025. And what that does is it's a lookout. First, what we do is we look at the way the world may look in 2025 and beyond. And then we develop concepts so we can fight, win, and achieve our national objectives in that environment. And understand that as a Marine Corps, we're expeditionary in nature, and that's how we look at it. We're naval in character, so we come from the sea. And we expect to fight in the littorals, probably in an urban environment with uncertainty and chaos related to that. And so we're experimenting with our concepts that will give us asymmetric advantages in that environment. So that's kind of getting big to small. So what does that mean is we have right now it's a 3-phase campaign of Sea Dragon. We just got done taking a hard look at our ground combat element. We fight as a Marine Air Ground Task Force where the sum is greater than its parts. And the base of that task force is the ground combat element. Next, we're looking at our logistics combat element, which is why AACUS is important, because we're looking at several components we're seeing about the future is manned-to-unmanned teaming, artificial intelligence, autonomy, machine learning. Those are the things where we say we better get involved, we better do it, or it's going to be done to us. So we're getting ahead of the game, looking into the future and saying, this is coming, the technology's there. You see much of it is off the shelf, and that our adversaries can do it. So we're looking well into the future and being ready for when the technology is fully mature and ready to be employed. How are we going to employ it? So to that end, we're going to take this technology and others, and we're going to insert them in our campaign. And it looks like this spring, we're going to take it out to 29 Palms, the service level exercise. We use live forces simulating how we're going to fight in the future. We're actually going to integrate the technologies and see what it means for us organizationally, how we have to train, man, equip differently, and what advantages it'll give us over an adversary. And then we'll continue it on through experimentation. Our next phase, we incorporate the information environment, electronic warfare, jamming, GPS denial, etc. And we'll move on to our further concepts for the future. And the end state is that we're set up in 2025 to be asymmetrically dominant in the way we see the world at that point. So we're really taking a scoop of the future, bringing it here now. And that's the so what behind seeing what you saw today. So any questions about the experimental process or how we do live force experiments or how we develop our concepts, that's my specialty. Thanks.
Rip, do you want to give the award?
Sure. So Fritz Langford, Aurora Flight Sciences. So what we witnessed today and what we demonstrated was a system autonomously planning and reacting to the environment as the aircraft flew through it. So we had a GCS operator entering in tactical control measures and a starting and ending location for a mission. We witnessed the aircraft do its autonomous path planning, both at a high level doing waypoint planning, sending that to the GCS operator for review, and then on the GCS operator's command, the aircraft executed that mission completely autonomously, and the safety pilot was just along for the ride. We witnessed the aircraft do obstacle detection and avoidance. So notably, in and out of the forward operating base, the system was detecting walls, towers, and those light posts in the forward operating base, as well as the tree line on departure out of the FOB, and doing obstacle avoidance and reacting to that environment. It did all of this while operating autonomously and with no prior knowledge of the environment, with no map and no survey overflight beforehand.
So I work with installation logistics as part of the Next Log team, and I'm the technology that AACUS has developed with ONR, and actually scaling it down to a smaller drone type package that you saw in the back corner in the display set up in the tent next door. So we're looking at those, scaling that sensor package down, the same everything down into a small package where it can actually be utilized by the ground logistics and infantry units organically. So it's just one of the examples of where this technology is actually branching off and used in similar capacities within the Marine Corps. We are partnered with the Army. We're working with McWheel with experimentation on actually injecting this in and learning how we can better employ autonomous technologies even down to the tactical unit level.
Chris, you want to say something?
And maybe just one more comment that I'll touch on that is that's a great example of how the technology that Aurora's developed on this program can scale up and scale down for different applications and to support the warfighter at different unit levels as well. And that the technology is easy enough to use that operators without extensive training and without an extensive course in operating the aircraft can interact with it and provide supervisory control to it through the tablet interface that we developed and through other interfaces that we previously demonstrated, as Dennis mentioned, through the radios, through the Crick 117s and other interfaces that we've integrated into the aircraft.
So again, my name is Corporal Osterhaus. I'm an infantryman by trade. I've been lucky enough to grow up in the Marine Corps where all this new technology has been growing exponentially, and it's been really exciting to be a part of that. Coming into the Marine Corps, it was the most advanced thing that we were seeing. We started testing out small quadcopters at the squad level, and now just a few years later, I'm controlling this autonomous aircraft via tablet from the ground. So any questions you have about the implications on the warfighter at the small unit level, I can do my best to speak to. It's pretty exciting to think about. As Lieutenant Colonel Cherwell can agree, the responsibility of the squad leader has been evolving very much so for the past 15 years. And the fact that you could potentially give this tablet to a squad leader and have him controlling what his squad needs, when he needs it, and where he needs it, it's really, really exciting. So it's been a privilege to work on this project, and I'm really excited to see the future implications.
Thank you. Okay, we're going to open it up now for questions.
Question for you, sir. You said that the aircraft in this particular demonstration, there was no prior knowledge of the environment. But this particular aircraft has flown in this setting, right? It has not landed in the zone before, or is it doing it for the first time?
So we had done testing on the Quantico range before we were out here last week, but when the system turns on, when we turned on the power at the beginning of the day, there was no map generated from that previous flight that was stored on the aircraft.
So when I'm trying to understand when it encounters new objects and when it learns from that environment, it is not storing it on the database?
We do store it for our analysis and for future use and refinement of the system. But one of the count-offs that was developed for this program was that the aircraft would be able to operate in a new environment, and the way that we simulate that is to clear out the memory each time before we turn the system on. When we turn the system on. So to the system, it's as if it's a brand new environment that it's never seen before.
Yes, sir.
Thank you. I have a question for Fritz and Colonel Schmidt. Fritz, I know that this system is designed for a cargo helicopter, but could it potentially be applied to, a troop transport like an Osprey or a gunship? And then Colonel Schmidt, do you see potential applications for using this on other types of aircraft, for example, gunship, troop transport, that kind of thing?
So, yeah, a note on the platform portability first is absolutely that this was designed as a platform agnostic system and was designed with portability in mind. And while we did the cargo resupply mission first, what we've really developed is a system that carries widgets, right? And so the aircraft in the LZ today can carry 2,000 pounds of widgets. So that could be water, it could be MREs, any sort of resupply, and and beyond that, it's a cargo and other utility mission platform, right? And so certainly I pass it off to the Colonel for comments on applications on that.
That's a great question, and it talks about how we look at the problem. So the H1 platform that it's on is merely a distractor for us from the experimental standpoint. We're looking at everything that it's possible to do, and we're completely not bent on one function such as logistics. So as the corporal says, the squad leader's job essentially is what battalion commanders did not too long ago. They handle all of the functions of the battle space: intelligence, logistics, command and control, fires. We're pushing all that down to the lowest level, and we have to simplify it and make it more cognitively intuitive, because we're putting such a burden on so many Marines. So this is important because how we see the future: smaller units spread over greater distances to drop below a targeting threshold. Because one of the characteristics we see is everybody has access to each other's factories right now through things like Amazon. We used to have discrete factories that we could put in Ohio somewhere, and only we had the thing or the item. That's not the case anymore. So speed of adaptation is really the measure of effectiveness. And what we believe is that our human capital, our raw product, our young Marines, are really our asymmetric advantage in how quickly they can employ the emerging technologies. So to get to the heart of your question is, what do we see it doing? The sky's the limit. We've already talked about a system like this dropping off smaller autonomous unmanned systems that release another autonomous unmanned capability. Picture a swarm that impacts the electromagnetic spectrum through jammers or collectors or GPS deniers itself. It's easy to talk about the logistics, the chow and the ammo and the blood plasma. That's just really the first step. Do we see it moving casualties? We're not saying no. Absolutely, we see it moving casualties, but there are policy and there are cultural and ethical implications to that we have to discover. So we're not limiting what the capabilities the autonomy gives us. We know that science and technology is moving that way to give us capabilities that our conventions may hold us back from. So we're breaking those conventions when we look at experimentation and see where it takes us. And what we found really is we have to cross our bins that we typically think of things logically. For instance, a system employing the AACUS technology may be on a logistics mission, but at the same time collecting electromagnetic information and feeding that to a targeting system that then employs fire. So is that a logistics mission anymore? So we really have to break down some of our bins and think about it in very broad terms on where we want to be asymmetrically dominant in the future and apply that way. So certainly from our perspective at the Warfighting Lab, it is not just logistics and cargo.
Colonel, when you take it out to 29 pump, are you going to take this system, or are you going to take something different to test this technology?
So at the risk of going beyond my technical capabilities, I'm going to take whatever the AACUS developers best think they can bring us, and we're going to employ it across the Marine Air Ground Task Force in as many capabilities or functions as we can get it in. So I can't tell you if it's this particular exact system or not. It's we know emergence will change things, and we're ready for that to change.
Okay, for instance, guys have said that you're using GPS in the system. The system could be designed to be GPS, in a GPS denied environment. Are you guys working toward that?
Yes, absolutely. So GPS denied navigation was it is a core technology and was a core research area of the AACUS program. And what that really comes down to is executing the missions today were conducted with GPS, but we've done extensive research, and we had results in back of the tent showing our progress on executing these missions without GPS as well. That we do not want GPS to be a limiting factor to the autonomy and to executing these missions.
Colonel, could you elaborate on some of the experimentation and kind of exercises you're looking to try out with AACUS? You mentioned 29 palms in the spring.
So we have a standard service level exercise of 29 bombs that has a lot of infrastructure to it, and we're used to sending units there, and that's really it's like a finishing school for combat. And what we're able to do in that environment is we're able to replicate what we think it may look like in the future. So what we're going to do is we're going to have disparate units handling all the functions of the battlefield at the small unit leader level. We're going to put a lot of weight on our NCO's shoulders, and they always ask for more and perform superbly with that. So we're going to actually jack up the pressure and the weight on them, not physical weight, but cognitive weight. We're going to put them at further distances, and then we're going to use advances in data management to figure out what their needs are, anticipate their needs are, and from a logistics standpoint, supply them first. We're also going to add how that can impact our operations in the electromagnetic spectrum with collections. And we're looking very hard at the GPS denied capability. We're pretty excited about that because one of the ways we can go is what we're at the low end of the experimental totem pole here. We're calling it mutually assured denial, where if everybody loses it, we think we can operate better than the rest of our competitors. Maybe today we can't because we have a heavy reliance on GPS that was an asymmetric edge for us for a while, but that calculus has changed. So we just have to change our stance to be able to operate better in that really dirty electromagnetic environment. So we'll be looking at that as well.
I'm sorry, could you repeat that phrase? Like, you said standard of service. What was the name of the location you used?
Our service level exercise.
Yeah, you said where it was, what you referred to as like the finishing school?
In 29 Palms, we call it integrated training exercise. And it's run year-round out there. 29 Palms is like our finishing school where units go and they apply all of their modern techniques and procedures.
Yes, sir. Yes, Colonel Mike Baby here from James. Things you mentioned at the very start was were naval character. So is this something you look for shipborne applications at some point in time? And if so, from the subject matter expert, what's the kind of extra difficulty or problems or whatever it's up to?
From a concept standpoint, if it's not shipborne, we're not really interested in it because we're naval in character. We are partnered with the Navy, and that's how we get where we need to go. And really, the maneuver from the sea is an asymmetric advantage that sometimes we lose sight of. We know we're expected to operate from the sea into the littoral, so I can't speak institutionally, but I can say from an experimental standpoint, if it can't be shipborne and they can't move us ashore, it's probably not in our
Is there any algorithms or whatever to make this work better on all ships?
Actually, that ONR has had programs that they've been working on to do that. It is a different environment, of course, since the runway is moving. So that does require a different type of algorithms or relative motion that actually have been developed and should be implemented in the future as part of the development of this program, or this technology and the program maybe in another form continues on. But that definitely is what the Colonel said. For the Navy and the Marine Corps, so if we're coming from the sea, it's always going to be part of our...
Is this something you can marry up, for example, with a fire scout? Or is that...
I'm sorry?
Is this something you can marry up technology like fire scout?
Well, like I say, we've got the platform agnostic, so whatever it is, we'll like to be able to work on it. You work within the limits of the aircraft, so whatever the aerodynamic limits of the aircraft, is what you're going to be limited.
Yes.
And I heard a comment on whether you have identified any cybersecurity issues with the system.
I can't. No, it's not working. We have no cyber testing as part of this program this far. But definitely that will be something as you move into engineering development of the program, that definitely would be addressed.
Yes, sir. Tony Hayes, Baltimore Post Center. Corporal Officer Houses. Could you talk briefly about the training with the tablet, one, and two, what did you see anything different today after actually using it?
Could you repeat that last part, sir?
If you saw anything today with this exercise that you didn't expect or want to have.
So my training, I've worked with Aurora, I think about 5 times over the past few weeks, and came out here, got a little demo of how the system works, learned about its application on the bird, and then we slowly moved into getting me some tablet time, and I'd say between 5 and 15 minutes, I had a great understanding of how this system worked. Me using that tablet to order in ASRs, supply requests, and whatnot. Training-wise, I mean, one of the easier things that I've learned in the Marine Corps thus far. I'm wholeheartedly confident that I could teach anyone down to private PFC, and within 5-15 minutes how to operate this tablet. As well as if someone were to become incapacitated for some reason, I'm confident that someone could pick this tablet up and figure it out on the fly, which is big in the warfighting community, because we all know the risks that comes with. Does that answer your question, sir?
Well, I guess the second part of the question was, did you encounter anything today that you weren't expecting?
No, we have done a few rehearsals, and from my understanding, everything went just how it has, how it's been planned. Yeah, yes, sir.
Well, we didn't just, we were, at the very beginning, we put CONOPS groups with Marines in it. It's part of the program. So we didn't just develop this, me and Fritz get together in a back room. We actually had the CONOPS working groups where the Marines told us what they would want in an ASR, a 9-line brief, how that would go out. So we were hoping that it would be very seamless. It would be very familiar to a Marine that picked it up. So that's one of the objectives of the program.
Thank you.
Corporal, could you, that question is very similar to what I wanted to ask you, but I wonder if you could answer it in a slightly different way. Okay. Could you describe what it is you actually did? I mean, you don't have the tablet in front of you, so you can't actually show us, but can you describe it? I mean, how does it compare to, say, calling an Uber?
Okay. Yeah, that's actually, I've used a few things to compare it to. I've compared it to a Domino's pizza tracker and Uber, but essentially on the tablet itself, I can specify what I want, where I want it, and when I want it. Type in a grid coordinate, or I can just have it pinpoint my location without having to type that in manually. Yes, sir. And then I hit submit. It's honestly that easy. You order what you want, when you want it, whether it's urgent or if you can wait a little bit, which is very important to whoever's controlling the aircraft in the battle space. They need to know how urgent you need it, But yeah, as far as the tablet interface, it's incredibly comparable to an Uber or ordering a pizza. Once you hit submit, you hit something called mission view, and it has where the aircraft is, when it's on its way to you, when it's about to land, and when it's on the ground. Once it's on the ground, I have control of the aircraft on that tablet. So once we offload those supplies, I hit clear the LZ. That means that the LZ is clear, that it's safe for that aircraft to take off. And once that's been cleared, I drag it across the screen. I swipe right, and as I do that, the bird begins to take off. So definitely, as we said before, something that's new to me, being a corporal in the infantry, something that I never would have thought I had control over. But not nervous at all. I'm confident in the system. It's definitely easy to use.
Any additional questions?
Sure. So one other additional comment on that is on the takeoff is that the system is autonomous from takeoff through landing, but in order to take off again, we did decide to require human interaction. So the beginning of mission requires input from the operator of the system. It's not designed to auto take off on its own. Although again, that's something that we can tweak as we work with Will on the integrating this with the Marines and with the Marine Corps Warfighting Lab to look at the best way to use this technology.
With Aurora's recent acquisition with Boeing, was there anything that was leveraged from Boeing into this project?
Well, the short answer is not yet. So the acquisition was like a month ago, so it has. We're excited to leverage those opportunities in the future and have started some of that work, but the bulk of the engineering work on this program was done over the course of about 5 years. I would note that we did actually fly on a Boeing aircraft in 2014 on the Boeing Unmanned Little Bird. This is not the only system we've demonstrated this. This is not the only platform we've demonstrated this system operating on in closed loop autonomous flight. We've flown on other aircraft as well, and one of them is the Boeing Unmanned Little Bird.
Mr. Langford, earlier it was mentioned that, an incredible amount of AACUS is actually COTS, which is, great and also scary at the same time. What components of AACUS did Aurora specifically develop as opposed to being COTS?
Sure. So the hardware is basically all COTS, and then most of the work went into software, went into the algorithms that are and the path planning, the decision making, and the sensor fusion. So utilizing the information that comes out of the COTS sensors and using it to make intelligent decisions, interact with the humans and with the operators, and then fly the aircraft.
I have a question. So you said there really not a map on board the aircraft. When the system encounters a new object on the ground, is it just simply treated as an object? For example, you did that demonstration of briefcase or box or what if it's a carcass or if it's some dead body on the ground or some other object, does it recognize it as an object, or how does it work? Or does it need to be changed every time to recognize a new object?
Yeah, so there's a couple different layers that are going on inside of the obstacle detection there. So the first layer is what we call geometric obstacle detection, and that is strictly looking for solid objects that you don't want to land the helicopter on top of. And then there's another layer that's going on that's looking for semantic terrain classification, that's looking at classifying the terrain based on properties like whether or not there's water there. So don't land in a muddy area, for example, because the skids will get stuck in the mud, that you'd rather land on the solid ground. And so there are a couple different layers there happening, and that's what it's doing on the inside of the landing zone evaluation.
And we have some of our other team members that also can answer more detail. They're part of the team.
Do we have any other questions? All right, well, ladies and gentlemen, thank you very much for attending today. Thank you to the panel.
Thank you very much. Thanks for coming.
By the way,